In the next few lectures, we'll be talking about acids and bases. We'll start off with, in this lecture, with the definition of an acid and a base, the Bronsted definition, and then we'll start using curved arrows to show how electrons rearrange themselves in acid-base reactions. And then we'll define briefly pKa and use that to understand position of equilibrium in acid-base reactions. So remember, hopefully, from general chemistry that at least we're going to start off by defining a Bronsted acid as a proton donor. So it's donating H+, and a base will be defined in the Bronsted definition as a proton acceptor. The conjugate base is the thing that lost proton on the product side. The conjugate acid is the thing that gained the proton on the product side. So be able to, and for any acid-base reaction, I want you to be able to identify the acid and the base, also the conjugate base and the conjugate acid. Notice in this reaction, HCl is donating a proton. Notice that the proton is gone in the product. Water is accepting the proton. It has an extra hydrogen in the product side. Similarly here, this guy is the base. This guy is the acid because this red hydrogen was transferred, or this proton, as we often refer to it, this proton is transferred from water to this base. So be able to identify your acids and your bases and your conjugate acids and your conjugate bases. What we're going to do in this class, which is probably going to be new to you, is we're going to use curved arrows to depict how the electrons rearrange themselves. In organic chemistry, what we're concerned with is bonds, and in reactions, bonds are rearranging. Bonds are composed of electrons, so arrows help us keep track of where the electrons were in the starting materials and where they end up in the products. This can be somewhat confusing because what we're not showing is where the proton is going. What we're showing is where the electrons are going. Just like when we were doing resonance structures, what we're going to do is always start the arrow on a lone pair of electrons or a pi bond. There are no pi bonds here, so we're going to start it at this lone pair of electrons, or this one, they're all equivalent. Notice if we look at the starting material, methoxide is the base, so it's accepting a proton. Water is the acid. It's donating a proton. Notice here we have 2 lone pairs on oxygen. Here we have 3. Here we have a new bond to hydrogen. Here we don't. So the first arrow that we're going to draw is a lone pair of electrons that are going to become bonded to a hydrogen. Okay? So this arrow is saying this lone pair of electrons became a bond to hydrogen. But notice what happens to our acid. It loses a proton. It donates the proton to methoxide. We have 3 lone pairs of electrons on oxygen here. Here we only have 2. We lose a bond to hydrogen. Here we only have 1 bond to hydrogen. Here we have 2. So this bond becomes a lone pair of electrons on oxygen. So these 2 arrows together describe how the electrons are rearranging in this reaction. Notice, this is exactly what I just drew. You have the lone pair of electrons becoming a bond to hydrogen. This bond breaks, and that becomes a lone pair of electrons on oxygen. So we're not going to worry too much about the mathematical definition of pKa. Remember, for any generic acid-base equilibrium, you have your acid, which is donating a proton. You have your base, in this case water, and that's going to form a conjugate base and a conjugate acid. If you have a strong acid, remember it's going to disassociate, and this side is going to be favored when you have a strong acid. If you have a weak acid, it won't dissociate very much, and this side is favored if you have a weak acid. So reactants are favored if you have a weak acid. Products are favored if you have a strong acid. Now, remember, we can describe an equilibrium constant by products over reactants. This is usually a constant, so we move it over to this side and we get a new thing which we're going to call Ka. The negative log of the Ka is going to be the pKa. All I really want you to focus on here is the magnitude of the pKa. So what you want to remember is large pKa is associated with weaker acids, and small or negative pKa's are associated with stronger acids. So if I give you 2 pKa's, notice that this is an equilibrium, right? We don't necessarily know off the top of our heads whether the product side or the reactant side is favored, but if we look at the pKa's, we can figure it out, because the equilibrium will always favor the weaker acid. So the side of the equilibrium that has the weaker acid is going to be the side of the equilibrium that's favored. So what's weaker here, water or this acid called acetic acid? Well, this pKa is smaller, so this must be a stronger acid. This pKa is bigger, so it must be a weaker acid. So this side, the product side, is favored. So the equilibrium will favor this side as opposed to this one. What about in this case? Well, let's look here. We have a pKa of minus 1.74 and a pKa of minus 2.9. This one is more negative, which means it's stronger. It's a stronger acid. This is less negative. It's a weaker acid. The equilibrium is always going to favor the side with the weaker acid, so this side is favored, or reactants are favored. So I want you to be able to use pKa's, if I give them to you, to determine which acid would be stronger or weaker, or which side of an equilibrium will be stronger or weaker. So for this lecture, what we talked about was defining Bronsted acids. Remember, a Bronsted acid is going to be a proton donor. A Bronsted base is going to be a proton acceptor. I want you to understand, what does pKa mean? Bigger pKa's mean weaker acids. Smaller pKa's mean stronger acids. For the rest of the semester, we're going to be using curved arrows to show how electrons are rearranging themselves in organic reactions. So this is something that you're really going to want to practice in class and on your own. And then we're going to start using pKa and other factors that we'll talk about in the next lecture to determine which side of an equilibrium is going to be favored. Remember that you can use pKa to compare acid strengths between two acids or even more acids, just knowing that the smaller the pKa, the stronger the acid, the bigger the pKa, the weaker the acid.